Hello students, in this video I am going to go through the derivation for the equation of a hyperbola. So a hyperbola is defined a little differently from the definition of the from an ellipse. Remember the ellipse, okay, had two foci, and the distance between any point on the ellipse to either of the foci, when added those distance up, they have to remain the same. Here, this is actually in reverse. And what do I mean by in reverse? So the distance, okay, between any point on the ellipse to either of the focus, the difference of those distances must always remain the same. So how is that? How can we express that, or how can we even figure that out? Okay. So just like before, okay, we can think of the extremes one more time. So the distance, okay, between, let's pick this point here as the rightmost vertex here as the point of interest. So the distance between the focus on the left will be a minus negative c. The distance between the point, the rightmost focus and that point on the right, okay, will be a distance of c minus a. The difference between d1 and d2 will be a minus negative c minus c minus a. And it is based on this rule, okay, that we're going to be able to generate an equation for the hyperbola. So let's take a look, okay? Just like before, I'm going to come up with an equation describing the distance between d1 and the distance between d2. So the distance for d1 is the distance between x comma y and the leftmost focus. It's given by this. And then the distance between the x comma y and the right focus is given by d2, which is this guy right here. The difference between these two must remain the same all throughout. It must equal to 2a. And just like before, okay, I'm going to try to get rid of the square roots, okay, by squaring both sides. But before I do that, I'm going to bring one of the square roots to one of the sides, to the other side, and then I'm going to square both sides. I am going to square the right side using structure because, you know, at this point we're really good at that. And I am going to eliminate the y squares. I will now FOIL out x plus c squared and x minus c squared because I noticed that there are going to be x squares and c squares that I can eliminate. So therefore, I can eliminate these guys. And I can combine the two xc's. I can combine the two xc's in the next step. And I'm going to subtract over 4a squared. Well, actually, no. I divide both sides by 4 before I subtract both sides by 4a squared. There's a common factor of 4. And now I'm going to subtract both sides by a squared. And in the attempt to get rid of the square root, I'm going to square both sides once again. I will now FOIL out the left-hand side, FOIL out the right-hand side. I'm going to distribute the a squared because if I do that, I can see that I can get rid of that term there. And indeed I do, right? I have those two terms are identical. I can eliminate them. And very similar to the derivation of the equation for an ellipse, okay, I'm going to bring over everything that has a variable and then bring over everything else that does not. So I brought over all the constants to the right, brought over all the terms with the variable on the left, And the situation becomes very familiar because here there's a common factor of x squared, and then by factoring out an x squared, we're going to see that the two expressions that I highlighted in blue will also have a common factor. I want to divide both sides by the entire right-hand side here. So thereby, I'm left with x squared over a squared minus y squared over c squared minus a squared equal to 1. So unlike the last derivation where we had another point to observe, there's no other extreme, because this is the only vertex that I have. These 2 points right here are the only 2 vertices that I have. There is one other trick up my sleeve, right? And that is, it's algebra, right? Anytime we can throw in a dummy variable to make things look a little nicer, we can certainly do that. So what I'm going to do is, to make this look nicer, I'm just going to call b squared equal to c squared minus a squared. Can we do that? Absolutely. We can call things whatever we like, just as long as we're not breaking any rules, right? So c squared minus a squared, okay, we haven't defined a variable yet. We're going to define that to be b squared. So the whole equation then can be re-expressed like this, where b squared is equal to c squared minus a squared. And even though this is made up, as it turns out, there is some significance to what b is in relation to the graph of the hyperbola. And that's actually left for another video.